Scientists now propose that the Moon is much older than previously believed, with a surprising history of intense volcanic activity that repeatedly reshaped its crust. These groundbreaking discoveries challenge long-held assumptions about the Moon's formation and evolution, while offering valuable insights into the early solar system. In this video, we will explore this revolutionary research, its significance, and what it reveals about the Moon's fiery past. New findings published in Nature estimate the Moon's age to be between 4.43 and 4.51 billion years, revising previous estimates that placed it between 4.35 and 4.51 billion years. This conclusion is based on a detailed analysis of lunar rock samples, particularly zircon crystals, which are highly resistant to heat and pressure. Zircon isotopes act as natural timekeepers, providing crucial evidence of when the Moon's crust first solidified. While most lunar rocks suggest the crust formed around 4.35 billion years ago, zircon data points to an even older Moon beneath a surface that has been geologically reset over time. Lunar rock dating relies on radiometric techniques, where scientists measure the decay of radioactive isotopes such as uranium and thorium into stable elements. This decay functions as a clock that only starts ticking once the rock cools enough to preserve its isotopic composition. The Moon's history of intense volcanic activity likely reset this clock multiple times, erasing evidence of earlier formations in most samples. This explains the discrepancy between the younger ages inferred from lunar crust samples and the older zircon findings. These discoveries are significant because they refine our understanding of the Moon's history and its role in the early solar system. Scientists believe the Moon formed following a massive collision between the young Earth and a Mars-sized protoplanet called Theia. The debris from this impact coalesced into the Moon, initially covered by a vast molten ocean of rock. Over millions of years, this magma ocean cooled, allowing the Moon's crust to solidify. However, the latest research suggests this process was not straightforward, but rather involved multiple episodes of melting and remelting that reset the geological timeline. Determining the Moon's true age is more than an academic pursuit. It provides essential clues about planetary formation and Earth's early environment, helping scientists understand the conditions that eventually led to life. One of the most striking revelations from this study is the scale of volcanic activity that shaped the Moon's early history. In its infancy, the Moon was much closer to Earth, orbiting at only a fraction of its current distance. This proximity generated strong tidal forces, creating friction that produced intense internal heating. This process triggered widespread volcanic activity, repeatedly melting and reforming the Moon's crust into a chaotic, molten landscape. A modern parallel to this phenomenon can be seen on Jupiter's moon Io, the most volcanically active body in the solar system. Io's elliptical orbit around Jupiter generates tidal forces that continuously heat its interior, fueling persistent volcanic eruptions. Similarly, the early Moon underwent tidal heating as its orbit transitioned from an elliptical to a more circular path. This internal heat caused large portions of the mantle to melt, with magma either reaching the surface or remaining trapped beneath, drastically altering the Moon's structure. Lunar rock samples and surface observations provide compelling evidence of this violent volcanic history. The Moon's dark basaltic plains, known as maria, are remnants of ancient lava flows that once filled large impact basins. However, new research suggests volcanic activity was far more widespread than previously thought. Internal heat may have liquefied vast sections of the crust, creating extreme conditions where even the toughest minerals, such as zircon, struggled to survive. This phase of intense volcanism played a crucial role in resetting the Moon's geological clock. As the magma cooled, magma that crystallized into new rock layers effectively erased evidence of older formations in areas where it did not reach the surface. However, heat-resistant zircons remained intact, preserving crucial clues about the Moon's early history. This duality explains why lunar samples often present conflicting ages. The immense scale of volcanic activity not only reshaped the Moon's crust but also played a key role in its chemical evolution. Volcanism likely released gases trapped in the mantle, creating a temporary atmosphere that may have influenced surface conditions. One of the long-standing mysteries in lunar science is the apparent discrepancy between the Moon's age and its surface features. For instance, the relatively low number of craters suggests a younger age, as older surfaces would have accumulated more impact marks over time. The new findings offer a compelling explanation. Lava flows from intense volcanism filled early impact basins, effectively erasing evidence of these collisions and giving the surface a younger appearance. Another enigma lies in the composition of the Moon's mantle, which differs significantly from Earth's. While both celestial bodies share a common origin in the Theia collision, the Moon's interior appears to have undergone additional chemical differentiation. Researchers propose that repeated melting events allowed certain elements to escape from the mantle into the Moon's iron-rich core, altering its composition. These processes align with the intense volcanic activity described in the study. These discoveries have significant implications for future lunar exploration. As space agencies plan missions to return to the Moon, understanding its volcanic history will be crucial in selecting landing sites. Studying subsurface regions with preserved zircons could provide valuable insights into the Moon's earliest days, while areas with extensive lava flows might shed light on its volcanic evolution. Ultimately, this research highlights the interconnectedness of planetary science. By studying the Moon's history, scientists gain deeper insights into the broader processes that shape planetary formation and evolution. This knowledge not only enhances our understanding of the Earth-Moon system but also informs the exploration of other celestial bodies, from the icy moons of Jupiter to the ancient plains of Mars. Thank you for joining us on this journey through the Moon's dynamic history. Stay curious and keep exploring as we enter the next era of lunar discovery. This study serves as a reminder that looking to the past is essential for shaping the future.